Welcome to this video on linear programming. We're going to try to conceptualize the topic here, but before we start, I'd like to say that a better title for this would be linear optimization. There is nothing that in any way whatsoever relates to computer programming here, and so it seems like a poor choice of name. But I'm keeping it because that's what all the other math teachers call it, so we'll stick with that. Here's the problem. I'll pause while you read. And the purpose of the beginning of this video is not to show you how to do the problems. I'll get to that later. Right now, I just want you to have a good understanding of what it is that is being asked of us on this problem. What you're about to witness in the first part here is not what you would actually do as a student solving one of these problems. Let's take the maximum portion of this question, for example. We want to maximize the function f given the constraints that are shown here. Just as an example, and again, you wouldn't actually do this, but just for consideration's sake, let's pose a hypothetical. What if x were negative 100 and y were 4? Would that lead to a maximum value of the function f? Well, let's find out. If I were to plug in negative 104 for x and y, and work this out on scratch paper, which I did, it turns out to be 118. So we've just discovered that for certain values of x and y, just random ones that I chose here, seemingly random ones, we've discovered that f, the function, has a value of 118. Is that the maximum? Is it possible for f to be any bigger than that? Seems like it would be. For example, if I chose negative 1,000 for x instead of negative 100, I'm quite sure that the result would be bigger than 118. But 118 is not even a candidate for the maximum here, because the x and y that I chose don't match the constraints of the problem. Let's go over the constraints one at a time. Did I choose a y value less than or equal to 4? Yes, I did. I chose 4. Did I choose an x value less than or equal to 7? Yes, I did. I chose negative 100. Did I choose x and y in such a way as that this constraint would be met? I recommend pausing the video now and seeing if that constraint has been met by our particular choice of x and y. Hit pause now. You should have discovered, just plugging in the x and y that we chose, that that constraint is indeed met. The last constraint, however, it turns out is not met. And just to show you why that is, here I've plugged in the two chosen numbers. And when I work this out, I get a false statement. Negative 196 is not greater than nor equal to 0. And so the concept of is 118 the maximum isn't even relevant, because I've chosen x's and y's that didn't meet all of the constraints. Again, I'm not suggesting you pick random numbers. There's a method for this, and we'll get to that later. What I am pointing out is that you have to choose values of x and y for which all of the constraints are true in order for it to even be a viable candidate for a point that leads to a maximum or a minimum value of the function. So the question now becomes, how can we go about this in a strategic, methodical way without having to pick random numbers and just hoping to get the largest possible value? Well, that's what this video is about, and that's what we're going to move on to right now. Oh, one more thing before we start. In order to fully understand this video, there is some requisite knowledge that you should have. It is the ability to graph systems of inequalities, such as the one you see here. I'm going to have you hit pause in a moment, graph this system of inequalities, which should be represented by a shaded region on a graph. When you're done, you'll hit play and see if you got the answer correct. Go ahead and graph this system now. Hit pause. You should have gotten this yellow shaded region as the answer corresponding to the solution of this system of inequalities. If this topic makes sense to you, then you're ready to proceed with this video. If not, I highly recommend that you go to my YouTube channel and look for the Linear Inequalities in Two Variables video before proceeding with this one. With that in mind, we'll now proceed to our first example. This example, in fact, is the very problem seen at the beginning of this video. Now let's go through the process of solving it in a more mechanical, reliable way. We're optimizing this function. That means we are looking for the absolute largest and absolute smallest value that f can have, given the constraints on the right side of the screen. So should we continue to pick values of x and y that match all those four constraints and just see how big or how small we can get the function f to be? I don't think that that's a very advisable path. And to be more methodical about it, I'm going to use a graphing approach. I'm going to graph the region that is described by the given constraints. And I'm going to use that region to optimize the function. Let's focus on the right side of the screen here. If we were to graph the equation that corresponded to this inequality, we would get this. For the second inequality, here's the corresponding equation, which I've graphed. For the third inequality, here's the equation, I've graphed that. And here's the equation corresponding to the fourth inequality. At this point, you would have to pick many random test points to decide where the shading was for each one of these inequalities individually. Ultimately, this shaded region that you see in yellow here is the overlap of all four of the individual shaded regions yielded by the inequalities. If this sounds way beyond your reach, go back, watch the video called Linear Inequalities in Two Variables referenced earlier in this video. Assuming you're okay with this yellow shaded region, let's proceed. Now, even though I've narrowed the values of x and y down to this one confined space, this shaded region, there's still infinitely many possible things x and y could be. X could be 0 and y could be 3. X could be 6 and y could be 2. X and y could be these values, or these, or these. Here, 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 or even decimal values. Well, how then, you might ask, am I going to go about essentially examining infinitely many values of f to see which one is the highest and lowest? Well, in a practical sense, you can't, unless we could rely on a discovery from prior mathematics. And it turns out there was such a discovery. You see, mathematicians have figured out centuries ago that the maximum and minimum of a linear function confined to a certain region of the xy plane must occur at one of the vertices of that indicated region. And so I don't have to try an infinite number of pairs x and y to decide what makes f the biggest and what makes f the smallest. I can simply find the value of f at all four vertices in this particular region. And then I know by that prior discovery that my maximum and my minimum for f will occur at one of those four places. So now I've reduced this entire problem down to finding the value of f at four specific locations. Let's make a table showing the value of f at each. Here's one of the vertices. I just chose that one randomly to start. And when I plugged in that x and y pair into this function, I did the work on scratch paper, not shown here, but the result was 19. You could do the same. Then continuing to the other vertices, I computed the value of f at each one of them in no particular order. I now know the value of f at the vertices, but I also know that the largest and smallest values here, which are 20 and negative 15, are not only the largest and smallest among these four, which of course they are. Because of prior discoveries in mathematics, we know that 20 and negative 15 are the maximum and minimum of this function, considering all the possible values of x and y. In other words, if I were to pick any x and y in this yellow shaded region, I would get an answer between negative 15 and positive 20 for the function f. My conclusion, therefore, is that 20 is the maximum of this function. We also say that the maximum occurs at the point negative 2, 4. Likewise, we've concluded that negative 15 is the minimum of the function f. We say that this minimum occurs at the point 3, negative 6. So out of all the stuff you've seen here in this problem, which portion of it is the answer? That depends on your professor, but in general, the answer is these four conclusions that we just alluded to. Now that we've finished the problem, let's go a little bit beyond the mechanics of solving these to give you a broader sense of how this topic works. First of all, let's consider the scenario where one of our inequalities, such as y less than or equal to 4, were switched in such a way that the shaded region became an unbounded region. Now, I didn't show the work here, but this shaded region that goes upward forever would in fact be the set of all solutions to this system of four given inequalities, if you were to take the time to actually analyze it using your inequality graphing skills. Now, you're unlikely to find a situation like this in a mathematics class, but it could happen. And when the region is unbounded, in other words, when the shaded region that contains all the allowable x and y values goes on forever in one or more directions, then the function may or may not have a maximum or a minimum. And if it does, it would occur at a vertex, but we don't even know in this unbounded case, in this forever region, we don't know if there even is a maximum or a minimum. And for this reason, you're unlikely to encounter this in most math classes, but nice to be aware of that fact nonetheless. Let's put the problem back to what it was originally and consider one more thing beyond the typical realm of this topic. What if we were to have a nonlinear function instead? Here's an example of a nonlinear function. You'll notice the exponents make it nonlinear. If we were to have a nonlinear function, how would we go about finding the maximum and the minimum? Would we once again plug the vertices in to this function and see which one gave us the largest and which one gave us the smallest? No, it turns out that's not a viable solution when your function is nonlinear. What do you do then to deal with the maximum and minimum of a nonlinear function? You use calculus. And it's not the purpose of this video to go that far. There's a chance that if you're watching this video, you haven't gotten to calculus yet, more than likely. So I won't attempt to show the calculus. But I think that I did do the calculus on scratch paper, and I think the end result is interesting even at this level. I discovered, when I did the work, that the maximum of this particular function is 51, and that maximum occurs when x is 3 and y is -6. So even though, as I stated a minute ago, the minimum or maximum need not occur at a vertex, this particular function's maximum did. By contrast, however, when I did the calculus, not shown here, the minimum of this function was 2. This function can't be any lower than 2, and it achieves a minimum of 2 at the point 3,1. You'll notice that is in the interior, definitely not a vertex of this region. When you get to calculus, you'll deal with nonlinear functions more regularly, but for now, suffice it to say that the trick that this video prescribes, the trick about plugging in the vertices to find the max and min, only applies when the function is linear. In summary, the first thing you'll do in a linear programming problem is you'll graph the given constraints as a shaded area. Then you'll find all the vertices. You'll then plug those vertices in to the function that you're trying to optimize. You'll look at your list of answers. Whichever one is highest is the maximum, whichever one is lowest is the minimum. And that completes this lesson on linear programming.